Good morning. We're just going to wait one more minute for people to log in. Good morning. We're just going to wait one more minute. Okay, let's just make a start, and this will be uploaded anyway. And I'll put it on Show My Homework. So, if you are year 10, you may have noticed on Show My Homework that a forces and balance test has shown up. Once again, you do have 2 weeks to do this and hand it in. Quite a few of you haven't handed in the last one. I'll get that marked for those of you who have done straight away. But it is important because if you don't hand these things in, we do have to chase them up. Alright, so let's start with resultant forces. Just as a brief recap, last week we mainly talked about what a force was. We talked about how a force is a push or a pull and is measured in newtons. We also talked about the difference between something being a scalar quantity or a vector quantity. Remember that a quantity in science or physics is basically just something about the world that we can measure, like time or distance or speed. Basically anything that can be measured and given a number, that's known as a quantity. And remember, scalar quantities, the direction in which this happens doesn't matter. It is just, here is a number that represents an amount and that is it. Such as your mass. You don't have a mass in a particular direction, you just have your mass. Time is just time. Speed is just speed. Distance is just distance. However, with vector quantities, it's basically a number but with a particular direction to it, such as displacement, your distance in a particular direction. Force is measured in a particular direction that it's acting. Now, let's represent these vectors, the force vectors specifically, with arrows. So I'm going to show you an example, and I want us to think about all of the forces that are acting on this object and in what direction they're acting in. And then we're going to clean it up a bit and then lead into what a resultant force is and why we need to use a resultant force in the first place. So, let me just make sure that my drawing tool is on the right one. Let's go with this, draw. Okay, let's say we had a car on the road. This is my car. It's not a very good car, but it is a car nonetheless. So let's say we had a car on the road. Now let's think about let let me just draw. This is the driver's side. There's my steering wheel, and there's my driver. Let's think about what forces are acting on this car. Let's pretend that it is moving forwards. He is driving, and it's moving forwards. So last week we learned about all the different types of forces, and now let's apply them to this scenario. So the first obvious one is, well, this person is driving forwards, so there's going to be some driving force. Oops. AKA thrust. Just so I don't have to write as much, I'm going to write thrust, having him go forwards. Well, the car also has mass, so it therefore also has weight, and that's going to pull them downwards. But remember, while the car is pushing against the ground because of its weight, the ground is also pushing against the car because of Newton's third law. There's going to be a reaction force. And this reaction force, even though it's usually forgotten, it is quite important, because without this reaction force, then that would mean that the car is just going to go straight through to the ground. My arrow might seem squiggly, but it should be straight. Okay, there are some other forces that are acting on this car. For example, as it's moving forward, there are going to be some resistive forces, aren't there? Like, he's touching the ground, and so there's going to be friction between the car tires and the ground. So I'm going to draw another arrow here to show friction. And there's also air, right? So there's also going to be air resistance pushing back alongside the car. And those are sort of the main forces that we can think of right now. Okay, so as you can tell from this diagram, it is a mess. And it's not just a mess because of my poor handwriting and my poor drawing skills. It is just, there's just so much information. There's just so much going on in this diagram. So, physicists, we don't like something like this. We don't like a diagram that carries too much information, a lot of which we don't need. So, what we do instead is we like to draw what are known as free body diagrams. So if I just scroll down a bit, we like to draw instead free body diagrams. Basically, instead of actually trying to draw and replicate the diagram and what it looks like actually drawing a car on the road, we like to just draw the object itself, and we don't even like to draw the object realistically. We either draw them as a square or a circle, basically, just to show, here is my object, that is it, we don't care about anything beyond that, we just need to know it is an object. And this is perfect for me because for those of you who have been with me through the entire year, you will know that I am not the best artist. So as a physicist, I am modeling a car as a circle. That's all I need to draw. That is a free body diagram. And the reason why we do this is because as physicists, we don't like to spend a lot of time on the actual artwork. We just care about the fact that it is an object. We only care about the forces acting on it. We don't need to know anything else. We don't need to know the make of the car, anything else like that. So free body diagrams just show the object as a circle, or if you prefer to draw it as a square or rectangle, you can, but basically simplify it as much as possible. I'm doing it as a circle. And then now we draw our arrows again. So our weight pulling it down, reaction, our thrust, and then air resistance, and friction. So already notice, let me just scroll up so you can compare this diagram versus that diagram. It's a lot clearer with what forces are acting on this. Just from the fact that we've cut out all of the unnecessary stuff. Also, one thing I want you to notice is that we didn't bother with drawing the ground, because with a free body diagram, we're just focusing on the one object and identifying with that one object what forces are acting on it. However, this is still not simple enough. We don't like this diagram. It's too complicated, because if you think about it, there are so many forces involved here. And if you think about any real life scenario, there are always loads and loads of forces acting on the same time on an object. There are forces acting on you as you're just sitting on your chair or wherever you're at. There are forces acting on any object. Even if the object is staying still, there are still forces on it, such as weight and reaction force from the table or the floor. So we want to simplify this even further. As physicists, we've thought about, okay, there are just way too many forces. We don't want to think about every single one of these forces and have to do calculations for every single one of these forces. That would just be too much. So how about if we can come up with one force that represents all of these forces? Can we do that? And the answer is yes, we can. We can represent all of these forces, combine them, and only have one force to represent every single force that is going on. And we call that force the resultant force. Now let's define it, because I know on your notes organizers we do have a section to define it, and is basically the sum or the net of all forces acting on an object. And this will make a bit more sense when we go on to an example with numbers. Okay, so let's do that. So I'm going to do an example that's a bit simpler. We'll only have two forces acting. Let's pretend we had an object. I'm going to draw a square this time. It's still a free body diagram. Let's say that you're pulling this along with two people pulling it together. One person's pulling it with 10 newtons of force. The other, and I'm drawing a longer arrow because remember the arrow length shows how big a vector quantity is, the magnitude. Let's say this person's pulling with 15. Well, there's two forces acting here, but we can represent, I'll put RF for resultant force, represent these two forces as just one force, combine them together. And with this example, you can sort of see that because the two forces are acting in the same direction as each other, why not just add them together? And that's exactly what we do. Instead of having two separate forces and needing to do two separate calculations then, whenever we calculate for forces, we can just represent it with one arrow, one resultant force, adding up together. And that is when it's in the same direction. Oops. Now what about if it's different directions? So let's say here we have someone pulling it with 15 again, and then another person, but pulling it in the opposite direction, 10 newtons. So this is why we learn about vectors and scalars to start off with. Because with a vector quantity, such as a force, the direction in which it's acting in matters. So here we have two forces acting in opposite directions to each other. We still want to find a resultant force. We still don't like having two separate forces that we have to deal with. Let's combine them together to make one force. It would be incorrect to say that the resultant force is 25 newtons again by just adding them up together. This is wrong. That's incorrect. Because these two forces are acting in opposite directions. So what ends up happening is we have to think about the overall force and the overall direction in which the force is acting. Now the resultant force, if you have a think about what's going on here, we have 10 newtons this way, 15 newtons the other way. The winning direction is going to be to the right. Winning by how much? It's winning by 5. The resultant force is 5 newtons to the right. So this is how you calculate the resultant force when things are acting on the same sort of one-dimensional line to each other. You can also go a little bit more complex, so I'll put an example up and maybe you guys can have a go. Let's say that we had there. Oops, that's not what I wanted. I know my arrow isn't as long as it should be. Okay, so let's say we had 15 newtons to the left, 15 newtons to the right. Let's think about whether or not there's going to be a resultant force here. Is there going to be a resultant force? Write in the chat, tell me what you think. Is there going to be a resultant force? Ignore my wobbly arrow on the left side. It should just be a plain arrow. Spot on, spot on. It is, resultant force is just going to be 0 newtons because they just canceled each other out. They, even though they're the same because they're the same number but going in the opposite directions, they've just essentially canceled each other out. Okay. Now I'm gonna have one that is a bit more challenging. I'm gonna do a circle this time. We'll say What's the resultant force? And direction. Oh, hang on. I shouldn't be doing this. Let me rub this off. Resultant force and direction. So, just to have a think about this, when it's the same line, 1 Newton, 1 Newton, they're in opposite directions, so going from the left to right, they cancel out. So there's no resultant force going in the horizontal direction. Now if we look at the vertical direction, we have 2 newtons going up, 6 newtons going down. So the overall direction, and here is how I recommend finding the resultant force, is first finding the direction. So the overall direction is going to be downwards. Downwards by how much? 4 newtons. So the resultant force is 4 newtons down. Okay. Now let's put this into context to help you understand. We can classify the forces acting on an object as balanced or unbalanced. And we saw these with all of the examples that we did. If the forces on an object are balanced, that means all of the forces acting in all directions sort of cancel each other out in a way, and then the resultant force is equal to 0. So as the example earlier that Ruben worked out, in this case, these forces, the 15 newtons left, 15 newtons right, those would be balanced forces. The resultant force is 0. And so what ends up happening is that there is no change to the object's movement. Just to help you understand what that means, no change to the object's movement, let me give 2 examples. Say there is, I'm going to not draw a free body for this one, I'm actually going to draw it out. Let's say there's like a box on a table. Box on a table, we have weight going down, we have the reaction force of the table on the box going up. These two are balanced, and so the resultant force is 0, and the box isn't moving. The box that is stationary is not moving. So anytime that you see something that is not moving, like your drink on the table, your books on the desk, whatever the case may be, anything that's not moving, you can know for certain that the resultant force is 0, because the forces, all of the forces acting on that object are balanced. Now, misconception, that obviously does not mean that there are no forces acting on the object. As we can see from our example here with the box on the table, there are forces acting on the object. There's weight and reaction, but all of the forces combined all cancel each other out to make a resultant force of 0. Now here's another example of balance forces and what I mean by no change to the object's movement. Let's say there was an object that was already moving, like a car. It's already moving in the forwards direction. And then we have thrust. I'm going to label that T. We have friction. And we have air resistance. Putting F for friction, AR for air resistance. Let's say that the friction and the air resistance, they can combine together to be the same amount as our thrust. So let's say that, if I redraw it again with numbers, because I don't want to overlay too much, let's say our thrust was 10. Our friction was 5, and our air resistance was 5. So once again, thinking about the resultant force, the ones going to the left, the forces moving to the forces acting towards the left, add up to 10. The forces acting to the right add up to 10. So they cancel each other out. The resultant force of this is 0. And one very, very common mistake a lot of students make is they think, right, the resultant force on this moving car is 0. That means then the car stops. That is incorrect to say. What the resultant force being 0 means to an object that already is moving is that there's going to be no change to its movement. It's just going to keep the same speed. It's not going to change unless some of the forces change. And so when it comes to balance forces, it's not that objects are fully stationary if it's balanced. It's not that the objects are fully not moving. It's that whatever that object is doing, whether it's moving at a certain speed or whether it's being completely still, if there is no resultant force that is not 0, it's not going to change its movement. This is a very important principle in physics that's going to come up in a later topic called inertia, which is all to do with Newton's first law. An object that is in motion stays in motion, an object that is still stays still. And that's why, like, just, slightly off topic, but still on topic, if you think about like astronauts who go out into outer space, in space, there's no air resistance because there's no like air particles around an astronaut. I'm going to draw it on this side, even though it's not to do with unbalance. So let's say we have an astronaut in outer space, okay? No air resistance, nothing. So, in outer space, let's say that we have our space station. Oh, I shouldn't draw it because I'm going to draw it horribly. Let's say that our astronaut leaves the space station and he doesn't tether himself, meaning he doesn't attach a rope to himself to attach himself to the space station. And he hops off the edge of the platform and decides to go for a little swim in outer space with no air resistance. So he's going to be moving. This is our astronaut. He's going to be moving in the forward direction to start off with because of that initial force that he gave himself when he launched himself off of the platform of the space station. Then later on, though, that force is no longer there. It was just an initial force that he launched himself off with. He's not providing any extra thrust or any extra motive force later on. Well, there's no air resistance pushing him back. There's no friction pushing him back. He's moving in the forward direction. I'm going to show this as movement. And there are no forces surrounding him to change its motion. So what would end up happening is that he would just perpetually drift into outer space, never stopping until he reaches some object that he crashes into, basically. That's why astronauts, when they go for what are known as spacewalks, where they leave the space station and go out into the outer space vacuum, they have that tether, so the rope around them, so they can be pulled back into the space station then, rather than get lost. Because you can't push yourself back, there's nothing around, there's no air to push yourself against, nothing. So in outer space, this astronaut would just keep moving until he dies, until he crashes into something. And the reason why I'm talking about this is because of the idea that in this case of the astronaut, the resultant force is zero because there are none of those forces acting on him. They're all balanced. The resultant force is zero, but he's still moving. He's not staying still because of the fact that he was already in motion in the first place, and there's no change to his motion unless another force acts. So when it comes to balance forces, really think about the fact that whether or not the object is already moving. Don't just think if the forces are balanced and the resultant force is zero, then that automatically means the object is stationary, is standing still. It might not be the case. Okay, now with unbalanced forces, the resultant force is not equal to zero. So it is some sort of number. And what that means is there is a change to objects' movement. So whether it be that, something that was still now starts to move, like you pick up a book by giving it a resultant force because you're exerting a bigger force on that book, so its motion gets lifted up. Or it could also, if an object is already in motion, it could either speed it up or slow it down. So back to my car examples. Let's say that thrust was a lot bigger than my friction and my air resistance. Thrust is a lot bigger. Well, that means that it's going to speed up in this direction, in the direction of the thrust. Here's another common misconception. Let's say as the car travels, it traveled a little bit at constant speed, and then the driver slowly hits the brakes. Thrust is less, and friction and air resistance is a lot bigger than thrust. I have seen this answer, and it is a very common answer. You look at these arrows and you might think, well, the car is going to go backwards. That is not true. Not true. None of you have ever seen or experienced a driver hitting the brakes and then the car all of a sudden traveling backwards. that doesn't happen. It's moving in the forward direction, but now the resultant force is this way. So what ends up happening instead is it slows it down. And this is all to do with the fact that the object is already moving. You'd be absolutely correct where if an object was stationary and these arrows were the same, then, well, yeah, it would go in, the leftwards direction. But if it's already moving and the resultant force is going to the left, it would slow it down to start off with. So unbalanced forces change an object's movement, whether it's changing it from being still, whether it's causing it to speed up or causing it to slow down. Whenever we have a change in its motion, we're talking about a resultant force that is not zero, that actually is something, and we refer to this as being unbalanced in terms of its forces. So, just as a quick summary, because we're about finished, and then I'll give you some practice to do. Oops. Okay, so just as a quick summary, a resultant force, very important that you know this key phrase, key word. Resultant force is the overall net force on an object. So if we were to represent all of the forces acting on an object with one force, with an arrow and direction, magnitude, and everything like that, we call that the resultant force. So it is basically the force that represents all of the forces that are acting on an object. If the resultant force is zero, then all of the forces acting on an object are balanced. That doesn't mean that they don't exist. They're still there. They just are balanced each other out. So there's going to be no change to motion. If an object is still, it's going to remain that way. If an object is moving, it's going to remain that way with the same speed. But if the resultant force is an actual number that isn't zero, like 1, 2, 0.5, whatever, if there is a resultant force that is not zero, then that means that all of the forces acting on the object are not balanced. They haven't perfectly canceled each other out. There is going to be a new force that represents all of the forces acting on the object that isn't zero, and that means that there is going to be a change to the object's motion, meaning it's going to speed up or it's going to slow down. There's going to be something about its motion that it changes, or it starts moving or stops moving, whatever the case may be. But there is going to be a change. We can calculate the resultant force resultant forces. Next lesson we're going to be calculating resultant forces when they're acting at an angle to each other. But so far, we have multiple ways we can calculate it. And depends on the scenario. So let's say that it's acting in the same line, and they're acting in the same direction. So as an example, if we have like that, basically it's like the same one-dimensional plane. And we have like 10 newtons, 10 newtons. The resultant force is going to just be added up together, 20 newtons. So you just add together But if they're in opposite directions, you do a takeaway, because you have to consider that they've done a little bit of cancelling. So if we had 10 newtons, 5 newtons this way, the resultant force is going to be 5 newtons to the right. And last lesson, we learned about how to calculate vectors when they are acting at 90 degrees to each other. So let's pretend that we had, and it's the same thing, you know, when you use Pythagoras to calculate displacement, same thing. Let's pretend we had 3 newtons this way, 4 newtons this way. What is the resultant force? Now, if you think about what is happening to this object, whatever the object is, think about, let's pretend it's stationary. What direction is it going to go? If you have one person pulling up, one person pulling across, well, the resultant force is going to be somewhere here. It's going to be somewhere in the middle that represents like the combination of a force moving it up and a force moving it to the right. There's going to be, it's a combination of the two, so it's going to be by here. Well, if you notice, we've made a little right angle triangle. And this is the same length as that. And so you could use Pythagoras to find the resultant force. Pythagoras, remember, is a squared plus b squared equals c squared. In this case, a is 3. 3 squared plus 4 squared equals c squared. This is just what we did on the first day. So our resultant force is going to be 5 newtons to the top right direction. So calculating the resultant force, you either add them together if they're on the same going the same direction. If they're in opposite directions, you subtract it from each other. And if they're acting at an angle, it is just like what we did when we calculated the displacement, because they're similar in that they're both vectors. You just use Pythagoras to calculate for the missing hypotenuse, and that would be the resultant force. Okay, now for a bit of practice, and I am going to put up the answers to this practice on the website. So let me just give you a quick link. Okay, so this should be found on the website Physics Paper 2 Resultant Forces. So you don't have to do all of these, obviously, but I'm going to put up the answers and just have you like do the ones you feel like you want a bit more practice on. Remember, this is entirely optional. What is mandatory are the topic tests and the educate that you have to hand in and do. This is just to help you get a bit of confidence. So if you're in year 10, remember there is a topic test that is on there right now for forces. I am just going to quickly put up the answers for you guys to see. Remember to download that document, because you're not going to be able to see, like Google Documents messes up the formatting a little bit. It looks a little bit freaky when it comes to Google Docs. So download it and open it with Microsoft Word. Okay, I've put up the answers now in the form of a PowerPoint, along with some notes as well to help you fill in your notes organizer. And then the answer should be on the very last 2 slides. Okay? If there are any particular answers where you're not sure how I got it, or you just want me to go over that one specifically, please let me know through sending me an email or leaving a comment on Show My Homework or leaving a comment on this video when it uploads. So with resultant forces, we should be able to get a bit of the practice done, and the more we practice finding the resultant force, the better we get at it. Okay. Right, guys, was good chatting with you. We'll see you tomorrow.